So, welcome to the course Mathematics of Generative Modeling, and we were developing various diffusion models, and we started with the evidence lower bounds. So, I will just do a quick recap of what we did. So, we started with log px, and then we proved derived a lower bound of this, and this lower bound was expectation of q x1 x0 log of p theta x0 x1 minus the KL divergence q xt x naught, and then p xt, and then minus sum over t equals to 2 to t, and then expectation of q xt x naught d KL, the KL divergence of q of xt minus 1 given xt x naught, and then compared with p theta xt minus 1 xt. So if you recall from the last class, we derived a bound like this, and we call this a reconstruction error. Then we call this a prior matching term. And then the remaining, this one, we call it denoising matching term. And then we looked into these terms, and then we are thinking how we will compute these terms. Okay, so in this we also assumed that all are normal distributions, and this makes computing the scale divergence possible in closed form, but these expressions were not that easy, so we used some Bayes rule, and then we derived a concrete expression for q t minus 1 xt x naught. Okay, so which is something we have derived exactly in the last class. So, and what we have found is that the expression for this is that it's also a normal distribution, although it was a bit expressions were long, but this was the whole point of the last class, to determine if this is normal, then what are its mean and variance. Okay, and then today we will see, we are assuming this also to be normal, so we will see what type of mean and variance we are going to assign to this denoising part, where we go from noisy xt to a denoised version at t minus 1. So last class we had this. Now today we will focus on this, and then we will derive an expression for the KL divergence of this and this, because both are normal. So we will use the formula for KL divergence when of computing two normal distributions, and so basically other things are in place already, we have seen previously. So this will more or less give us a full picture and the algorithm for various diffusion models, and then we will see certain variations in these in some of these how do we do the noising part, okay, and so on. So there will be 2-3 variants of these denoising models that we will see, and that will more or less capture all the recent most of the recent algorithms that we have in the diffusion model. Okay, so moving ahead, I will just write down the expression for this just to recall a little bit what was this, and then also we will write an expression for the p theta, and then we will do a KL divergence of this. So let us continue. So what we had after the derivation is the following. So we applied the Bayes rule to kind of flip this. Okay, then we had x xt minus 1 and so on, and then we had the terms in the numerator, other terms in the numerator and denominator, and we did all those calculations, and then we will just write down what we found in the last class. So xt minus 1 given xt x naught, and this was found to be a normal distribution. So xt minus 1 is the sample, and the mean and the variances are given by alpha t 1 minus alpha bar t minus 1 xt, and plus square root of alpha bar t minus 1, 1 minus alpha t, and x naught, and all this is divided by 1 minus alpha bar t, and then we had the variance term, which is 1 minus alpha t, 1 minus alpha bar t minus 1 divided by 1 minus alpha bar t, and then it's with the identity. So we had this as a mean. So if we write this mean, so this is mu q, we denote this, and this is xt, x naught. It depends on xt and x naught here. Okay, this is how the mean is, and then the variance, we denote it as sigma q at t. Okay, so this is an expression we derived in the last class, and now obviously we are looking at this term here where we say that what would be the KL divergence of this, and we also want to know what expression this has. Okay, although we know that it's a we want to model this as a normal distribution, but we want to know what could be the parameters for mean and variance. Okay, so first things first, we recall the KL divergence between two distributions. Okay, the closed form expression. So recall that the KL divergence between two Gaussian distributions, okay, is given by so that is a DKL, and first one is a normal with sample x, mean mu x, and variance sigma x, and then it's computed with normal with samples y, mean mu y, and variance sigma y, and then we close this parenthesis. So let us say in general we have two normal distributions given, and we want to find a closed form expressions. Well, it's well known. In fact, I believe I have done this in the previous classes. So in any case, like this could be checked, that this will be log of mod of sigma y divided by sigma x minus d plus trace of sigma y inverse sigma x plus mu x or mu y minus mu x transpose sigma y inverse mu y minus mu x close. So this is the closed form expression for KL divergence between two normal distribution. So this is where we have a focus on, where we have to compute KL divergence between q xt minus 1 given xt x naught, and then p theta xt minus 1 given xt. Okay, so this is what we are supposed to calculate. So we will use that formula, but then we want to know what is this p theta xt minus 1 xt. So one of the things that we would like to do is what we'll do is that of course determining p theta is like we have to provide mean and the variance. Okay, that's when a normal distribution is defined. So what we do is that we say that the variance of this guy and matches the variance of q basically. Okay, so that's something we impose. So let's say the variance of p theta is equal to the variance of q xt minus 1 xt x naught. Okay, so if we do that, then the variance term is kind of out of picture, and then the differences will be with the means here. Okay, so with this what we will get is so we set the variances of the two Gaussians to match exactly. So that's something we assume here. So we'll put the variance equal. Now then in that case the KL divergence will have certain reductions here. So let us see what it could be. So I have to use this board now, and then I'm going to rub this now. Okay, so So continuing, we have the KL divergence between the Q and the P that we had. So let us, and we are supposed to minimize that. So we have argument over theta of the KL divergence between Q xt minus 1 given xt x naught, and this is compared with P theta xt minus 1 given xt. Okay, so with our assumptions that the variance is the same, we have arg min theta and then dkl, and this is the normal distribution x t minus 1 mu q sigma q t, and then compared with normal distribution xt minus 1 mu theta and sigma q t. So as you can see, we have matched the variance terms, so they are now the same, and we have this mu theta, so we allow the mu theta to kind of predict mu q. Okay, so we want to see what this expression will look like now. So this, because we know the closed form expression, so this is arg min theta and then half of, so we use the formula that we wrote for the KL divergence there. So this is a log of sigma q t divided by sigma q t, because the variances are the same, so that would go away later on, and then minus d, and then plus the trace of sigma q t inverse. Okay, so and sigma qt and plus, and then so we have done the trace term here, so this is sigma q and again sigma q, because sigma x and sigma y are the same, which is sigma q, and mu y in our case is mu theta, and then mu x is mu q. So we continue then, we have mu theta minus mu q transpose sigma variance and then inverse, and then mu theta minus mu q. Okay, so we have just used the formula there, and there's nothing new here. So and then we will look at the simplification. So for instance, this guy becomes 1, so this will become log 0, so that term will go away, and then if you look at the trace, so this is identity, and then q is sigma is a d-dimensional, so it will be an identity matrix of dimension d. Okay, so this is identity matrix of dimension d, and hence if you take a trace of this, the sum of the diagonal entries, then it will be a d. So this d and that d gets cancelled, and then we are left with the last term. So we have to see, so I can write this additional step, and we have half and then log of 1 minus d, as I said this is plus d, and plus mu theta minus mu q transpose sigma qt inverse and mu theta minus mu q. So this d gets cancelled, and this becomes 0, and hence we are left with arg min theta half and then mu theta minus mu q transpose sigma q t inverse and then mu theta minus mu q. So this is what we are left with, and what we recall from the last class is that sigma q t was sigma square small sigma qt squared. Okay, so this is something we did in the last class, so we will bring in that, and hence we will have small sigma q identity inverse. So basically the sigma q should come out. Okay, and so basically the sigma square will be there and that will come out. So let's see the further simplification of this. So we will put that sigma qt that we obtained from the last class, and this will become arc mean of theta, and then half, and then mu theta mu q transpose sigma q squared t identity inverse, and then mu theta minus mu q. So we'll bring in this sigma square outside. So this is arc mean of theta 1 by 2 sigma q squared t, and then this is mu theta minus mu q 2 norm squared. Okay, that's what we get. So here we have used a shorthand notation here. So basically here where mu q was mu q xt x naught, and mu theta was mu theta xt t. So what we really want is that the mean of the denoising process, which is given by the mu theta, matches the mean of the q, which is basically the noising process. Okay, so basically we want to predict the noise that that was added. Because if we can predict the noise, then we can subtract that noise and get the denoised version while we go back at one step in time. And so basically this is what it means. So this means, in other words, in text, we just want to write this down. In other words, we want to optimize a mu theta xt t that matches mu q xt t. That's what we want. And now we recall mu q that we derived from the last class, and then we will see what could be a good choice for mu theta. We recall mu theta that we had derived previously, or mu q, I mean mu q xt x naught, and this was found to be square root of alpha t 1 minus alpha bar t minus 1 xt plus square root of alpha bar t minus 1 minus alpha t and x naught, and whole thing was divided by 1 minus alpha bar t. So now the question is, what should be our choice of mu theta? Okay, so what we observe is that mu theta also conditions on xt. Okay, and so given an xt, we are kind of trying to see what could be xt minus 1. Okay, so what we see here is that we want to compute the mean from xt. Okay, and that's what q is here. Okay, so from in the mean of the q is given by this. So from here, what we guess is that since mu theta is also conditioned on xt, it makes sense to keep this term intact. And obviously we don't get to the original image, but this part is something we may have to predict in some sense. Okay, so basically we will parameterize this by some predictor function which will try to predict this x naught. Okay, that's a hypothetical prediction function, but that's how we want to model this problem. Okay, so this is the intuition we have, is that the mu theta is also conditioned on xt. So basically using xt, I have to create a new mean. Okay, so of course this could be subtraction of some variance terms or addition of certain variance terms or so on. Okay, or it could be addition of some other terms, but the point is that, okay, we can still use this xt. Okay, and then just see what could be a good choice for to replace x naught. Okay, so So with this intuition, now we can write down what could be mu theta. So as mu theta xt also conditions on xt, we can match mu q xt x naught closely by setting it as follows. So as I said, the plan is to keep the first term and then kind of predict the second term. So let us do that. So this is mu theta of xt. T is square root of alpha t, and 1 minus alpha bar t minus 1 xt plus square root of alpha bar t minus 1 1 minus alpha t x hat theta xtt, and whole thing divided by 1 minus alpha bar t. So as you can see, the first term we kept intact. It is the same one, and even these coefficients are intact. The only thing we changed is that x naught is replaced by x hat theta. Okay, so basically we want to say that we have some prediction function that predicts x naught. Okay, so and this theta that we see here will be parameterized. So the one of the good predictors we have these days are neural networks. So we will use some form of neural networks. So where x hat theta xt t is parameterized by a neural network that seeks to predict x naught from the noisy image xt. And at time index t. So with this choice of the mean that we have, now we can put this in the KL divergence expression, and then we will see what this means. So this implies that arg min of theta dkl q xt minus 1 xt x naught p theta xt minus 1 xt. So we will put this expressions for the mean there. So we saw in the previous derivation that we ended up with mu q minus mu theta norm squared. So so if we put this expressions for mu theta and mu q, then we have, so we'll write it a bit smaller. So this is arg min theta of 1 by 2 sigma q squared t, and then this is square root of alpha t 1 minus alpha bar t minus 1 xt plus square root of alpha bar t minus 1 1 minus alpha t x hat theta and xt t, and whole thing divided by 1 minus alpha bar t, and then I subtract it with square root of alpha t for the theta term, mu theta 1 minus alpha bar t minus 1 xt plus square root of alpha bar t minus 1 alpha t 1 minus alpha bar t, and then this is 2 norm squared. So that's what we had. Previously we just put the expressions for mu q there, and let's check it's okay. So square root of alpha t 1 minus alpha bar t minus 1 xt plus then root of and x hat. So the first term was the mu theta term, and then subtracted by the mu q term. So it seems to be correct. And now we will simplify a little bit. So some cancellations will happen. So obviously what we see is that the first term for both these guys were the same. So the first terms do get cancelled. So we will be left with the difference of the second terms. Okay, so let us do that. So as I said, the first term gets cancelled. So we have arg min theta 1 by sigma q squared t, and then we have norm of square root of alpha bar t minus 1 minus alpha t, and then x hat theta xt t divided by 1 minus alpha bar t, okay, in the denominator. And then we have square root of alpha bar t minus 1 minus alpha t x naught, then divided by 1 minus alpha bar t, and we have this norm squared. So as I said, the first term got cancelled, and now we will take this, even these terms are common, the coefficients before this x theta hat and then all the terms before the x naught are the same, so we will take that common. So then we will get arg min of theta alpha bar t minus 1 minus alpha t have x hat theta xtt minus x naught norm 2 squared. So you've taken that common, the common terms, and then we will take this out also from the norm. So if you take this out of the norm, it will be a square. So the next step is arg min theta 1 by 2 square t, and then it becomes a square. So this is alpha bar t minus 1 minus alpha t squared divided by 1 minus alpha bar t squared, and then whole thing is x hat theta xt t minus x naught squared. Okay, so this is what we have as a final, as a simplified form. So what we observe is that optimizing the variation diffusion models, and essentially the last term, okay, the prior matching, the matching term we have, that involved KL divergence between these guys, and that eventually leads to this. So minimizing that term KL divergence is now equivalent to saying that I have a prediction function that predicts the original image. Okay, so how bad is my predictor? Okay, that's so essentially everything boils down to this. So we can write this fact that hence optimizing KL boils down to learning a neural network neural network to predict the original image, predict the original ground truth image from an arbitrary. So ground truth image in our case is x naught from an arbitrary and nullified version, which is let's say the x theta. Okay, so it's from an arbitrary nullified so we will be at a stage where we are at t and we are at a nullified step, and then we want to see whether we can, from that time t, the nullified image we have, can I predict the original image x naught. What we also observe is that this is a minimization over time t. Okay, but then this would be true for all time steps. Okay, so because this is t is kind of arbitrary here, so for a t I want to predict the x naught, for some other t also I want to predict x naught. So we can take an expectation over all t time steps. Okay, and we can see this as an expectation where t, the time step, is the random variable here. Okay, it's like I pick any time step t, and if we want kind of like our predictor to be so good that from any time step t, it kind of predicts x naught. Okay, for some other time step t, again it predicts some x naught and so on. So basically, we can compute this over all time step as an expectation over t, and t we can choose to be some uniform distribution. Okay, so with this we can now change this to an expectation computed over all times 0 to t. So if you recall, the reason why we want to do this is that we had the summation term in the original the denoising matching term that we had. There was a summation over t equals to 2 to capital T, and this is just one term of that. So just for your convenience, I will write down that term. So recall the denoising matching term. So denoising matching term, and this was, so on the whole, this was t equals 2 to t, and then this was expectation of q and xt given x naught, and kl of q xt minus 1 given xt x naught, and p theta xt minus 1 given xt. So this is what we were trying to estimate, and then what we wrote down until now is this term, the KL divergence between q and p theta, and we found out that doing so is equivalent to minimizing this basically. Okay, so x theta hat minus x naught, and here if you look at, then this is kind of taken sum over t equals 2 to t. So this is kind of some kind of an average, okay, over from t equals 2 to t. So we can remove this summation term. Okay, so it's like a weighted average. So we can remove this summation term as an expectation over t. Okay, so that's what we are trying to say here. So let us write down this inwards, and then we will put another expectation over t. Okay, so minimizing this, summation term across all noise levels So remember that in our case the noise levels are T. Okay, so across all noise level T can be approximated by minimizing the expectation, right? So can be approximated by minimizing the expectation over T. Okay, so hence we will now change this sum term by an expectation over T, and T we will take it to be uniform. So with this, our minimization problem becomes our mean over theta, and then we, as I said, we take expectation of T and we consider this to be uniform, and this is taken from 2 to T. Okay, and then we have the other terms as before, so I will just copy it from my notes. So the xt x naught dkl q xt minus 1 given xt x naught, and p theta xt minus 1 given xt. Okay, so there is an expectation outer, so we can also put one more parenthesis. So this is expectation for all these guys. This could be kind of estimated or optimized using stochastic samples, because at each time step we will have these noises and so on. Okay, so we can have this estimated over many of these or some of these time samples. Okay, we can pick some of these time samples and then we will try to estimate this. Okay, so so now given that we have this view that okay, denoising process, what does it mean, and then eventually how the expressions look like and how we are going to compute them. Okay, so what is left is learning how the diffusion noise parameters, which are, if you recall, alpha t, how we will set those things. Okay, so let us look into this, learning diffusion noise parameters. So we want to so if you recall, the coefficients that we had, which are denoted by alpha t, that is used to in the forward process to make the images noisy. So one of the things that we said in the previous discussions is how do we kind of choose those alpha t, right? So one possibility is like we make it learnable as well, but then in the beginning we said that those are not really we don't want to make the forward process a learnable process. So just to put in the notes, so one, so how the noise parameters, so we want to now answer this question, how the noise parameters of VDM can be jointly learned. Okay, so this is the question that we want to. So one potential approach is that model alpha t using a neural network. Let us say alpha hat and eta t, where eta t are the parameters of the neural network. So this is one possibility to learn this alpha t. So so let us look into the expressions that we had previously when we were deriving the K divergence term, and then from there we will so that will give us some hint on how to kind of estimate these alphas. Okay, basically we will use something called signal to noise ratio. So let us continue with where we had in the derivations to see what could be done for these alphas. So this sigma square t, if you recall, and this is alpha bar t minus 1 minus alpha t squared divided by alpha bar t squared, and this is x hat theta xtt minus x naught. So I just copied over what we wrote previously, and then we will do some arrangements, and we will lead our derivations to something called signal to noise ratio, and from there we will get some interesting idea about how to kind of learn these noise parameters. So we do these simplifications. So I can kind of like so there is one sigma square t term here, right? So that term I will just substitute here basically. Okay, so this is 1 by 2 1 minus alpha t 1 minus alpha bar t minus 1 divided by alpha bar t, and then we have alpha bar t minus 1 minus alpha t squared 1 minus alpha bar t squared, and then we have x hat theta xdt minus. So we have just substituted the sigma q square t term there, and then some cancellations we can see already. So this is equal to 1 by 2 1 minus alpha bar t divided by 1 minus alpha t 1 minus alpha bar t minus 1, and then alpha bar t minus 1 minus alpha t squared alpha bar t, and this is x hat theta xtt minus x naught norm squared. So we just done this some additional step and then we will do the cancellations in the next step. So this is equal to half of alpha bar t minus 1 minus alpha bar t and divided by 1 minus alpha bar t minus 1 minus alpha bar t, and then x hat theta x dt minus x naught squared. Okay, we did the cancellations here, and then we have this simplified term. Now we will continue with this. We'll write it as a difference of the signal to noise ratio. So what we'll do is that we will add and subtract some two terms here. Okay, so this is equal to half alpha bar t minus 1. So we will do subtract and add, which is alpha bar t minus 1 alpha bar t, and then plus of alpha bar t minus 1 alpha bar t, and then minus alpha bar t, and then this all this divided by, so all this is divided by 1 minus alpha bar t minus 1 minus alpha bar t, and here we have x hat theta x t t. So this is now equal to, now we will split this into two. So this becomes half, and then basically we will take alpha t minus 1 and we will take alpha t terms. And so alpha t minus 1 term, if I take a common, alpha bar t minus 1 common, then 1 minus alpha bar t minus alpha bar t minus alpha bar t minus 1, and whole thing divided by 1 minus alpha bar t minus 1 minus alpha bar t, and then this is x hat theta x dt minus x naught. So then we split this into two. So this is alpha bar t minus 1 minus alpha bar t divided by 1 minus alpha bar t minus 1 alpha bar t minus alpha bar t, and then 1 minus alpha bar t minus 1 minus alpha bar t. So this is the splitting we did, and then we have x hat theta xt So we have done this splitting, but we also see some cancellations here. So 1 minus alpha bar t, this guy gets cancelled, and 1 minus alpha bar t minus 1, this gets cancelled. Okay, so there is this last simplification that is needed, so I will write it there. So then the previous expression reduces to alpha bar t minus 1 divided by 1 minus alpha bar t minus 1 minus alpha bar t 1 minus alpha bar t, and then x hat, and then xt t minus x naught. So this is the expression, reduced expression we have, and if you look into the recall the expression q xt x naught, then it was a Gaussian Okay, so if you recall this QST x naught, then this was assumed to be a Gaussian of this form, and we can define a signal to noise ratio. So define noise ratio, which is also usually called SNR, and this is equal to mu square by sigma squared, the square of the mean, and then the square of the variance, I mean the variance itself. So at each time step we have this signal to noise ratio. Okay, so hence SNR at each time step t is given by SNR t is alpha bar t divided by 1 minus alpha bar t. So basically we look here, and this is our mu and this is our sigma. Then this is how we are defining the signal to noise ratio here. So mu square by sigma square, and with this we can now write this as SNRT minus 1 minus SNRT. Okay, that's the plan. So let us do that. So we can put that as an star. So continuing from star, so we have so we write the initial terms to 2 sigma square qt alpha bar t minus 1 minus alpha t squared divided by 1 minus alpha bar t squared, and this x hat theta xtt minus x naught, and this is now in terms of SNR. I can write this as SNR t minus 1 minus SNR t, and then we have x hat theta xtt minus x naught squared. This formulation is now is interesting in few ways. So with this view of signal to noise ratio, we can write few sentences on this and how this will help. Okay, so overall what we want is that this, as we go in the forward process, then we want we want that there is no signal at all. Okay, so basically in the forward process we are looking at x0 real image, we add a noise x1, then we get x2, then we get x3, and ultimately we get to xt, which we want it to be standard normal. So with this signal to noise ratio formulations, what we want is that as t is increasing, we want that there is no signal and it's a pure noise, and that's when that's the ideal case that we have. Okay, so we want to create a fully noisy standard normal following a standard normal distribution. So so it's good to write down these few lines about signal to noise ratio. So some remarks. So SNR obviously represents the ratio between the original signal and the amount of noise present. Right? So this is what we know. This is exactly the definition of SNR. And in diffusion models, we want this SNR in diffusion models so we require that the SNR monotonically decreases as time step t increases. Okay, so this is what we want. So as time step t increases, we want the noise to be signal to be less and less, and noise to be, so the variance will capture the noise. So variance is significant and noise is signal is going to 0 and the variance is significant, hence we will expect that the SNR overall, the ratio of signal to noise will go to will monotonically decrease. Okay, gradually it's becoming more and more noisy. So this also means that the perturbed input that is but the perturbed input becomes noisy, increasingly noisy over time. and until it becomes a standard normal, right? That's what is the expectation, until it becomes standard Gaussian or normal. Okay, so these are the few remarks that we have. So with this view that these SNRs are supposed to be like that, this also gives us some ideas. So the ideas here would be what would be, let's say, um, what would be the modeling for the I mean, SNR themselves involve these alphas, right? And what we are trying to see in this section is what are the good ways to choose this alpha, right? And by modeling this problem into this difference of the SNR, what we are trying to say is that this is giving us some hint on the choices of alpha. Okay, so the fact that I want my SNR to be a monotonically decreasing, okay, then maybe this is a good model from where I will try to estimate the alpha that I need to create the noises, right? So this means that just by looking at the SNR, we wonder what would be a good property of an SNR. It should be monotonically decreasing, but it should be something perhaps that we can also calculate. Okay, so the way to way to look at this is, let us think of some function that that has this behavior that it's monotonically decreasing. Okay, and eventually let us say asymptotically when t is large, it becomes 0. Okay, so one possible function could be, let's say, exponential with the negative power. Okay, so e to the minus x would be a possible choice for SNR. Okay, so this is the hint that we will get, and we can also parameterize this exponential e to the minus x. So we know that with x, in our case it will be, let's say, exponential e to the minus t, but that itself may not be a good right, so may not be a good, so this is like, let us say, exponential e minus t. So as t increases, exponential of e to the minus t obviously decreases and it becomes close to 0. Okay, that's fine, but then so I'm supposed to calculate these alpha 1, alpha 2, and so on. So it may be that it may be that exponential itself is not a perfect, although I know that the form of the function will be like that, it should monotonically decrease, but I don't know it will be exactly e to the minus t. It could be some function of e to the minus t, and that function itself kind of, as t increases, that function increases, and so on. Okay, so one possibility is that we change this to e to the minus let us say omega t, so some function of t. Okay, and at t increases, if w omega t increases, then this also gradually decreases, but the decrease will be not necessarily like minus t. It may be something else, but it is still exponential, but then the decrease rate or something may be different depending on the problem at hand. So hence we don't want to say that this is exactly e to the minus t, okay, because there may be a variations given the problem at hand. So what we do is we say that it is decreasing, which is modeled by exponential minus, and then we say that this is something we are not sure about, so we can put a parameter theta eta here, okay, some parameterized function here, and that parameterized function will do a good prediction of the power of the exponential to choose. Okay, so that will make that will give us a required flexibility in not just decreasing these, but also decreasing it with some good estimates in hand. Okay, so that's why we will now model SNR as exponential of minus omega t. Okay, now what is eta is something we have to, and what is omega also we have to see, right? So it seems like, since we are saying it's a prediction, so omega could be some prediction function. Okay, so whatever you are aware of, let's say linear predictor, neural network predictor, so we may have to choose that, and those linear predictor have some weights, usually theta. So here we are saying the weights are eta. Okay, so this is what we will do as the next step, is that we will say that SNR is exponential. Okay, so we can represent as follows. So as I said, I will do SNR of t as exponential of minus omega or w, let's say w eta t, where omega or where, so let us call it omega, okay, so small omega. So omega eta t is modeled as a monotonically increasing neural network with parameters eta. Okay, so just to read it, if in case you cannot read it, so where omega eta t is modeled as a monotonically increasing neural network. Okay, so it should be increasing with t, so that overall exponential will decrease with t, and that is what is needed. The monotonic decreasing property is needed for SNR, and we need this monotonic decreasing property because we want to make signal to noise ratio go to 0, and that's when we will get the final image as a completely noisy image. So this is the plan. So if we say that SNR is modeled like this, so we know that SNR is defined as the ratio of alpha t minus 1 divided by 1 minus alpha t, and so on, right? So from there we know what is SNR in terms of alpha. We will substitute that here, and from there we can solve for the alpha. Okay, so let us do that. So so we know what is SNRT. So then we have, so this implies that alpha bar t divided by 1 minus alpha bar t. So this is the SNRT, and this is equal to exponential of omega nt. So from here we solve for alpha bar t is sigmoid of minus omega nt, or from here we can also say that 1 minus alpha bar t, we can also write it as sigmoid of omega t. So these are the two terms which we can compute as a sigmoid. Okay, so sigmoid, if you recall, it's a sigmoid is 1 divided by 1 minus e to the minus x, right? So sigmoid okay, so sigmoid stands for that. So these are the expressions for alpha bar t and 1 minus alpha bar t that we can compute via this sigmoid function. So with this, then we have certain interpretations for this. So we have these computations of alpha bar t and 1 minus alpha bar t given as a sigmoid and so on. So we will write down combining all this, we will write down some algorithm later on. Before doing that, we want to do some interpretations of the various diffusion models we have. So there are like 3 different interpretations that I'm going to discuss next. So and this will also lead us to some new ideas. So we have 3 equivalent interpretations, and this also leads us to some new variants of diffusion models. So what we recall is that the variational diffusion models can be trained by simply learning a neural network to predict the original image. So that we have seen the original image x naught from a arbitrary noisy image xt. X naught has 2 other equivalent parameterizations. so which leads to different variants of VDM. So firstly, we can use the reparameterization trick. So in our derivation of the form of q x t x naught, so what we have assumed is when we were deriving, if you recall, q x t x naught. So if you recall this, we did this, that what is the distribution xt given x naught, okay, with certain choices of alpha t and scaling of the means and the variance, translation of the means and the variance. And we have done this derivation before, and with that we could say that so we had derived that the xt follows, xt is equal to square root of alpha bar t x naught plus 1 minus alpha bar t epsilon naught. Okay, so this is what we derived before. So from here we would like to see how x naught looks like, okay, and see what could be interpreted from there. So solving for x naught, we solve for x naught, then we have x naught is xt minus square root of 1 minus alpha bar t epsilon naught divided by square root of alpha bar t. So with this choice of x naught, we will now plug it into the term we had for the mu q, right? So plugging this in true denoising transition mean, which you recall it was mu q xt x naught. So which we recall it to be like this: square root of alpha t 1 minus alpha bar t minus 1 xt plus square root of alpha bar t minus 1 minus alpha t x naught, and divided by 1 minus alpha bar t. So this was the mu q xt x naught that we derived, and here we can plug in x naught, right? So you can plug in x naught and see what this mean comes out to be. So this will be equal to, so we'll just put this x naught there. So this will be square root of alpha t 1 minus alpha bar t minus 1 xt plus square root of alpha bar t minus 1 minus alpha t, and then we have substituting this x naught 1 minus alpha bar t epsilon naught square root of alpha bar t, and then whole thing divided by 1 minus alpha bar t. So we have just substituted x naught from here, okay. So this x naught is now substituted here. All right, so let us see what it leads to. Okay, so after substituting this, then we have simplifications of this. So let us see what is that. So square root of alpha t 1 minus alpha bar t minus 1 xt 1 minus alpha t, and then xt minus 1 minus alpha bar t epsilon naught divided by alpha bar t. And then so the simplifications I did are xt 1 minus alpha t 1 minus alpha bar epsilon naught and divided by 1 minus, yeah. So continuing, we have this is like we get a cancellations of alpha. Here we can write this as alpha t times alpha t minus 1 square root. So then we had this 1 alpha bar t minus 1. Here we have 1 alpha bar t minus 1 got cancelled, and hence we have alpha square root of alpha t remaining here, and then this is whole thing divided by 1 minus alpha bar t. Now what we'll do is that now we will separate out these three terms. So this is alpha t 1 minus alpha bar t minus 1 xt divided by 1 minus alpha bar t plus 1 minus alpha t xt divided by 1 minus alpha bar t square root of alpha t minus 1 minus alpha t square root of 1 minus alpha bar t epsilon naught divided by 1 minus alpha bar t square root of alpha t. So we have split these three terms, okay? So if you see the first term, square root alpha t, 1 minus alpha bar t minus 1 xt divided by this, and then we have 1 minus alpha t xt divided by 1 minus alpha t, and then this square root of alpha t is also here, and then similarly we have the, and then with this is with xt, and then this is again going with this. Okay, so far this is good, and we see that there is an xt common, so we can take this common. So this is square root of alpha t 1 minus alpha bar t minus 1, and then plus 1 minus alpha t and divided by 1 minus alpha bar t, and this is divided by 1 minus alpha bar t square root of alpha t, and this is now taken common by xt, and then we have minus of 1 minus alpha t, and then square root of 1 minus alpha bar t epsilon naught divided by 1 minus alpha bar t square root of alpha t. So the last term we didn't do anything, we only took a common for xt here. Now after taking common, this term will get simplified. So we will write the simplified. Continuing from here, we will do the simplification of the first term. So we have simplified the first term. As you can see, you can easily see that some cancellations happened, and I leave it up to you to verify. And then we also have further cancellations of alpha t here. So this leads us to 1 minus alpha bar t divided by 1 minus alpha bar t square root of alpha t xt minus 1 minus alpha t square root of 1 minus alpha bar t square root of alpha t epsilon naught. And here again we have further cancellations going on, so that's nice. So this also gets cancelled, and then here there is no cancellation in the second term. So then we have 1 by square root of alpha t xt minus 1 minus alpha t divided by square root of 1 minus alpha bar t square root of alpha t epsilon naught. So continuing from there, we would like to finalize that. So then by looking at this term here, this is an expression for x naught, right? We started with x naught, and we arrived here, and what we see is that one of the hint that we have for the choice of x naught is that we have this term, and then we have this epsilon naught. Remember, the epsilon naught is the first noise, Gaussian noise, standard normal Gaussian noise that we have injected in the image. So we can view x naught now as follows, where we will now predict the epsilon naught. So we can therefore approximate the denoising transition mean mu theta xtt as follows. Mu theta xtt is 1 by square root of alpha t xt. So you are looking there. So we are keeping the first term intact, and we are going to parameterize a function to predict epsilon naught. So this will be minus 1 minus alpha t divided by 1 minus alpha bar t square root of alpha t and epsilon hat xtt. So this is the prediction function that we have. Okay, this is a prediction function parameterized by theta, and if we have this choice of mu theta, the predicted mean of the denoising process, and then we can again look for the KL divergence with this mu and mu theta and mu q, and we want to see how how does the KL divergence look like with this choice, right? So hence the corresponding optimization problem becomes, so then we continue from that arg mean theta and then KL divergence of q xt minus 1 given xt x naught. This is the ground truth, and p theta, this is the one we want to predict. From xt we want to go to xt minus 1, we want to denoise, and with this choice of the mu theta and mu q, we want to see what does this scale divergence look like. Substituting the normal distribution form of this mean of theta KL and xt minus 1, the sample mu q sigma q t, and this is compared with normal xt minus 1 mu theta and sigma qt. Remember that we keep the variance same, so that's why it remains sigma q here. And so this is the optimization process, and then we know that this gets replaced by this distance is like 1 by 2 sigma square and then norm of mu q minus mu theta squared, right? So we have done that derivation, so we will use that now directly. So arg min of theta 1 by 2 sigma square q, and this is norm of alpha t xt minus 1 minus alpha t square root of 1 minus alpha bar t square root of alpha t epsilon hat theta xtt, and then minus the mu q term, right? So this is, let us write here, so 1 minus 1 by square root of alpha t xt plus 1 minus alpha t square root of 1 minus alpha bar t and square root of alpha t, and we had epsilon naught. Okay, we have written the third term below, and so this is what we have, and we want to kind of simplify this and see what does it reduce to. Okay, so once again the first term being same, they get cancelled, and then we are left with these two terms. So now it will fit in the board. Arg min theta 1 by 2 sigma q square t, and then 1 minus alpha t divided by 1 minus alpha bar t square root of alpha t epsilon naught, which is this term first. We have written this term first, and then minus of 1 minus alpha t square root of 1 minus alpha bar t square root of alpha t, and then epsilon hat theta xtt. Okay, so let us check that everything is fine. Basically the first term got cancelled and I didn't do anything, so we have yeah, the last term is the plus, so hence we wrote it first. So 1 minus alpha t divided by 1 minus alpha bar t square root of alpha t, and then epsilon naught minus 1 minus alpha t. So everything seems fine. Okay, so this is what we have, and then since these guys are common in front of alpha naught, and this guy is common, okay, in front of epsilon theta, so we are going to take that common and take it out also and make some further simplifications. So continuing from the last expression, we have we will take that common term, and then we had epsilon hat theta and xtt, and we can use the norm itself. The parenthesis is not needed, so basically this is norm squared And then we will take this constant term outside the norm, and since it's a square, it will become a square. So 1 by so I have taken this constant out, and then we can substitute the sigma q if you want. So or we can leave it here, and so what we observe is that with this choice of x naught that we wrote, okay, where we saw this x naught as a parameterized form from xt, and then from there we got to this epsilon naught term, right? So what we see when we compute the Cayley divergence for that choice of x naught is that now it's about approximating the noise that you had in the beginning itself. So remember, in a forward process we had the noise. So this is x naught, x1, x2. So this epsilon naught is the noise that you injected in the first time. So basically the problem now reduces to, can you predict the noise that you injected in the first time step, okay, using some parameterized network, okay, from any step xt that you are, okay, so maybe any step xt that you are, okay. So this is a different interpretation of the Cayley divergence between mu q and mu theta, okay. So so we can write few lines in the words. So here epsilon hat theta xtt is a neural network that learns to predict the source noise x naught, right? So this is what we said, the source noise epsilon naught, that is the standard normal epsilon sample 0 identity, okay. So this is the source epsilon naught that eventually determines, let us say, or is responsible for xt at time step t. So from here, this expression we can interpret this as predicting the first level noise, okay. So this is what just I'm going to write this. So we have shown that learning VDM by predicting the original source image x naught is equivalent to learning to predict the noise. And empirically, people have found that learning to predict the noise gave better results, okay. So and if we look into the, so we had the first interpretation where we are learning to predict the real image x naught. So we had x naught minus x hat theta and so on. And this is our second interpretation where we see VDM as a process of learning the original source noise from a given time step t, okay. So that's our second interpretation, and our third interpretation can also be useful. So the third interpretation comes from so-called Tudy's formula, okay. So this is Tudy's. I will use this as a formula right now, and maybe skip the derivations of this formula later on. So what this formula says is that states that the true mean of an exponential family distribution given samples from it can be estimated can be estimated by, so continuing, can be estimated by the maximum likelihood estimated, can be estimated plus some correction terms involving the score function or score of the estimate, let us say score of the estimate. We can I can go into the detail of the Tudis formula a bit later, but I will use this as a formula for the moment, and or maybe you can pick this up as a project. So what this essentially says is that, so mathematically for a Gaussian variable z that follows normal z mu z sigma z, Tudis formula states that Tudis formula states that expectation of mu z given z is z plus sigma z gradient of log pz. Okay, so this is how like the conditional expectation mu z could be obtained. So expectation of mu z given z will be z plus the sum of these gradient of log pz. So in this case, obviously in our case we may want to predict let us say the true posterior mean that we have. Okay, so this is basically q xt x naught, that the term we have. We would like to see what this this Tudis formula will lead to. Okay, we apply on that. Okay, so all this will lead us to some other interpretation in terms of the gradient of the log and so on. Okay, so I will let you know what this score means here. We apply this to predict the true posterior mean of xt given its samples. So what does this mean? This all mean is that the posterior means that we had was this term q xt x naught, and this we believe is that, or we have actually written this down before, is that square root of alpha bar t x naught and 1 minus alpha bar t identity. So this is what we know. This is how the q xt given x naught means. But we may ask, using the Tudis formula, what would be mu xt? Okay, given what would be the prediction of the mean given that xt is there. So then, by Tudis formula, we have expectation of mu xt, and this is equal to xt plus 1 minus alpha bar t grad xt log of p xt. So we apply the Tudis formula. In place of z we have xt, and then we have the variance. So the variance in this case is 1 minus sigma ti, and then that gets multiplied with the log of z. In our case, z is xt, so it's log of p xt. Okay, so we will write, for notational convenience, we will write grad xt log of p xt as grad log of pxt. Okay, just for notational convenience, we will drop this grad xt term as a subscript, and we just write grad. Okay, so now with the TDS formula, the best estimate for the true mean xt is generated from mu xt, which is given as this guy, right? So we have that this is the mean is square root of alpha t x naught. We know that. So with this, combining these two facts, that what we want and what TDS formula will give me, they should match. So this is what we are going to use that. So then by TDS formula, we have expectation of mu xt given xt is xt plus, by TDS formula we will just write down the expressions for directly, this guy equals, so let us do that. So square root of alpha bar t x naught must match what is given by TDS, which is 1 minus alpha bar t grad log of p xt. And from here we will solve for x naught, and this gives us another view of how x naught looks like. Okay, so as you can see, we are looking into various formulations of x naught, and from there we predict what could be the predictions we are going to do. In this case, it seems like the prediction is going to be for the log p xt, right? Okay, so let us solve for x naught, and from there we have x naught, which is xt plus 1 minus alpha bar t grad log of px divided by square root of alpha bar t. So we have solved for that, and now with this x naught we will now plug into the ground truth that we have done in the previous variants. So then plugging x naught into our ground truth denoising transition. So our denoising transition was, if you recall, mu q xt x naught, and then we will get mu q xt x naught is square root of alpha t 1 minus alpha bar t minus 1 xt plus square root of alpha bar t minus 1 minus alpha t x naught divided by 1 minus alpha bar t. So we have just written this mu xt x naught. Now we will substitute the x naught from here. So let us say this is double star. Okay, so let us substitute that here. So continuing from there, so we have plus square root of alpha bar t minus 1 alpha t, and we substitute the x naught here. And then whole thing divided by 1 minus alpha bar t. We have just substituted x naught there. So let us check. Its x naught is xt plus 1 minus alpha bar t grad log p xt divided by square root of alpha bar. And the first these terms are the same. Okay, so continuing from here, obviously we expect some simplifications. So this is so basically similar to what we did before. So this guy is square root of alpha t alpha bar t minus 1. So 1 alpha bar t minus 1, 1 alpha bar t minus 1 gets cancelled from there. So then we are left with just in the denominator square root of alpha t there, and that's the first step. So let us do this. So square root of alpha t 1 minus alpha bar t minus 1 xt plus 1 minus alpha t and xt plus alpha bar t 1 minus alpha bar t, and then we have 1 minus alpha bar xt plus 1 minus alpha bar t and grad log pxt divided by square root of alpha t, and whole thing divided by 1 minus alpha bar t. So so as I said, we just did this cancellation thing here. So I just see this alpha t here, nothing has changed. We are doing step by step, so that okay. So now as before in just the previous variant, we will split this into 3 parts. So this will be alpha t 1 minus alpha bar t minus 1 xt divided by 1 minus alpha bar t plus 1 minus alpha t xt divided by 1 minus alpha bar t square root of alpha t 1 minus alpha t 1 minus alpha bar t and grad log pxt divided by 1 minus alpha bar t and square root of alpha t. So we have basically separated these 3 terms. So you can see it's correct. Yeah, all the terms are correct. So then again similar steps, take xt common. So this is so with the xt common, we have square root of alpha t 1 minus alpha bar t minus 1 divided by 1 minus alpha bar t, and then plus this guy 1 minus alpha t divided by 1 minus alpha bar t square root of alpha t, and whole thing taken common by xt and plus, and the second term remains as it is, or 1 minus alpha bar t gets cancelled, right? So 1 minus alpha bar t here gets cancelled. So eventually this this becomes 1 minus alpha t exactly. So it's 1 minus alpha t by square root of alpha t and then grad log pxt. Okay, and then in the common term there are some cancellations happening. So if we see those cancellations, then cancellation happening with the alpha t. Okay, so basically this alpha t, take the add these guys, then if you add these guys, then this is common obviously, but then this is the 8, so this gets multiplied with alpha t, and alpha t 1 alpha t gets cancelled. Okay, so let us do this. So this is basically alpha t minus alpha bar t plus 1 minus alpha t. So if I do this, okay, so there are these simplifications, and then divided by 1 minus alpha bar t and square root of alpha t xt, and then plus the last term alpha t square root of alpha t grad log of pxt, right? So you can do this simplification, okay, multiply in that, and you get this, and then further there is cancellation happening here. So this is very similar to the previous derivations that we did. So we have this. So with this we have a further simplification, and this is equal to 1 minus alpha bar t divided by 1 minus alpha bar t square root of alpha t xt alpha t divided by square root of alpha t grad log pxt, and which further simplifies to, because this guy gets cancelled again, and this simplifies to 1 by square root of alpha t xt plus 1 minus alpha t square root of alpha t and then grad log pxt. So with this choice of this is our ground truth, and with our choice of the x naught, this is the ground truth expressions that we got. And by looking at this reference, as we did in the previous cases, by looking at this we will set our mu theta, the denoising transition mean. So so then hence, so in this case we will try to predict this, right? So you can already guess now. So hence we can set the denoising transition mean, which was mu theta xtt, mu theta xtt. This is our denoising transition mean, and this we will set it to be equal to so as usual we keep the first term, we keep the coefficient, and we try to predict this. Okay, so then we will get 1 by square root of alpha t xt plus 1 minus alpha t by square root of alpha t and s theta xtt. Okay, so now we have a prediction for this guy now. This is being predicted by this guy. Okay, so at some point we were predicting the x naught, at some point we were predicting the epsilon naught, and now we are saying that we are trying to predict the grad log of pxt. So these are like different ways to train the VDM by depending on which approximations or predictions you are going to do. So if we have this choice of mu theta, then we want to know what how the KL divergence looks like. But the equations for the KL divergence will be now like very similar. So we will kind of do this very quickly. So hence the corresponding optimization problem becomes argmin. So we are now looking into the KL divergence. We have this new transition mean, so we will just plug in those expressions now. So we have done this before, so this is like similar steps going on here. So this is dkl normal xt minus 1 mu q sigma qt and normal of xt minus 1 mu theta sigma theta. Okay, so with this we will now substitute theta. So then we have done this calculations where this is 2 sigma q square t, and this becomes norm of the difference of the mean. So in our case this is alpha t xt plus 1 minus alpha t square root of alpha t s theta xt t minus 1 by square root of alpha t xt minus 1 minus alpha t and then grad log of pxt. So let's create a space a little bit here. So pxt okay, so this is our ground truth level with the choice of the ground truth mean that we have, and using the Curies formula we derive this, and then this becomes our ground truth, and this is what we want to do the prediction for. And obviously the difference is in these terms. So everything like before will get cancelled, things will get cancelled like this here, and then these common terms will be taken out, and eventually in the norm we will have s theta minus log pxt, right? So this is what we will leave things here. So this is how we interpret this variant. And this is so as I said, I will take this guy common, so let me kind of do that. So maybe it's good that we do it on the other board. We continue from the previous step, and as I said, I will take this common term out. So this will be theta 1 by 2 sigma q square t 1 minus alpha t square divided by alpha t, and this is s theta t minus grad log of p xt to norm squared. So this is the interpretation we have. So here again s theta xtt is a neural network parameterized by obviously theta, and it learns to predict. So this neural network, it learns to predict score function. So this is what we call score. Okay, the score function log grad xt. So now bring that original notation that we had, we dropped it here, but we just bring it here for preciseness. So this is log of p xt, which is nothing but gradient of the log likelihood, right? So this is gradient of log likelihood with respect to xt, obviously. So xt, and for arbitrary noise level, right, at t, right? So the t is arbitrary for arbitrary noise level t. So as a few steps, final steps, so couple of lines we will wrap up for today. So we want to see how this log pxt relates to, let us say, epsilon naught, let's say, okay? Because earlier we had done some derivations where we were predicting the epsilon naught by epsilon hat theta, where theta was some parameters. So here we want to see, is there any relationship between this log p xt and epsilon naught. So that's what we will do, and then I will stop for today. And so our first remark, and the second remark is that the score function, which is log p xt, looks similar to source noise epsilon naught. So in case you are not able to see this, we will try to kind of derive this. So from the so we can prove this, right? So from this formula, so what we had, what we have is x naught is, so basically what we are trying to do is we will match the Thury's formula with the reparameterization trick, right? So in the reparameterization trick we had we had the epsilon naught term. So let me quickly verify that. So from the reparameterization trick that we had xt is, x naught is xt minus square root of 1 minus alpha bar t epsilon naught divided by alpha bar t. Okay, so this is, recall, reparameterization of that we used to obtain qxt from x naught. So this was the first expression we had, and in the second expression we had the xt computed from the Thury's formula, right? So in the second case we had x naught also equal to so this is from let us say from reparameterization. So and from Thury's formula we had another variant of x naught, which was xt plus 1 minus alpha bar t grad log of p xt divided by square root of alpha bar t. So we have two equations. So this is our 1 and this is our 2. So from here 1 and 2 we can try to see we can equate this and see what is the interpretation of pxt in terms of epsilon naught. So equating equations 1 and 2, we have xt plus so recall that sometimes we put subscript, sometimes we drop. Okay, it's just a convenience. So this is equal to xt minus so now with this equation we will solve. There will be cancellations obviously, so these guys are getting cancelled, and xt terms will also go away, both sides, and 1 minus alpha bar t. Okay, there is 1 minus alpha bar t, there is a square root there, so that's the only difference. So this implies that if we solve, then we have grad log of pxt is equal to minus 1 by alpha t epsilon naught. The relationship between the score function and the original noise. Okay, so what we will do is that we will just write down 2-3 remarks on this, and then we will wrap up for today. So remarks. The two terms in this case are grad log of pxt and the original noise epsilon naught are of, or they differ, okay, if you want to say it's differ, by a constant factor. Okay, that scales with time, that varies with time basically, that scales the score function measures how to move in data space to maximize the log probability. So so as we see in the source noise is usually added. So if you look into the epsilon naught term, then this is the original source noise added. And this guy is the negative of some scaling of epsilon naught. And this is what we need basically to denoise, right? So if we have added a epsilon naught noise, then this can be interpreted as going in the negative of that with some scaling. Obviously, in this case, scaling is 1 by square root 1 minus alpha bar t. So this can be interpreted as the noise that I added. If I'm going to denoise, then intuitively it's going to be subtraction of the noise with some scaling, and that's what we are trying to do here. So we can kind of put this as a remark as well. So intuitively, since the source noise epsilon naught in this case is added to the natural image x naught, basically to make it noisy, and moving in the opposite direction is what this represents. Okay, moving in the opposite direction. So we can say that this direction is given by 1 by a square root of 1 minus alpha bar t and epsilon k. So we can think of this as the direction that we're talking about. Going this in this direction denoises the image. Okay, that's what we are trying to learn. Okay, denoising process. So this going in the direction denoises the image just as a final remark. And so all this means is that learning to model a score function is equivalent to modeling the negative of the source noise. Okay, up to a scaling factor. So So this is what we have for today. We have concretely written the KL divergence between the ground truth and then the predicted distribution. So, and then we kept the variance same, and we allowed the mean to the transition mean to change. And when we did that, then we have three different interpretations where we try to approximate the original x naught real image, and then in the next interpretation we solve from the reparameterization trick. Then we say that it's essentially equivalent to predicting the original noise. And then as a third variant, we have seen that using the Twittish formula, it's equivalent to predicting a source, predicting a score function basically. And then furthermore, we have seen that looking at the score function, it seems that it's negative of some scaling of the epsilon naught. And this has an interpretation in the sense that epsilon naught is the noise that I add, and hence I will subtract some negative scaling of that noise. So with this unified setup, we will then look into some small variations of this. So for instance, we will look into score-based generative model. So we will have some remarks on score-based generative model, and then we will have some remarks on the guidance-based approach, which is used in some of the recent apps, and then we will look into the classifier guidance. So this will take perhaps one more class to wrap up the story on diffusion models. So with this, I will stop, and thank you.